In this video, we'll look at changing rates of change. Here is a flask that already has some water in it, and a pitcher full of water. I'll play an animation showing the water being poured from the pitcher into the flask. As you watch the animation, think about the relationship between the height of water in the flask and the volume of the water that is added to the flask. In particular, you'll need to determine whether the rate of change of height with respect to volume is constant, increasing, decreasing, both increasing and decreasing, or something else. I'll start the animation now. The answer is that the height of the water in the flask changes at an increasing rate with respect to the volume of water that is added to the flask. Let's think about why this is. First, we'll zoom in so we can see the flask in a bit more detail. Next, I'll represent the height of the water in the flask. I'll use a yellow oval to show the water that was in the flask before starting to pour. I'll represent the height of the water that was initially in the flask using a yellow line. And I'll represent the change in height of the water in the flask using a blue line. Next, I'll represent the volume of the water that gets added to the flask using a red arrow. Let's rewind this to the start of the pouring. Now I'll show this again. As the animation plays, think about how the height, the length of the blue bar, and the added volume, the length of the red arrow, are changing with respect to each other. Next, I'll add black bars to indicate the change in volume. So on the bottom, the distance between the bars is showing the amount of change in volume. We can copy this length onto the height bar. Now, if we think about the amount of change in height, we can see that delta H is roughly 1 1/4 as large as delta V. Let's rewind the animation. Let's play the animation again, this time incorporating the black bars to show the amount of change in volume. At first, when the amount of change in volume, the distance between the black bars, was small, the amount of change in height, the length of the blue bar, was only about 1/10 as large as the amount of change in volume. Later, when the amount of change in volume was large, the amount of change in height was about 1.25 times as large as the amount of change in volume. This is what it means to have an increasing rate of change. In this scenario, we say that height varies at an increasing rate with respect to volume if, for successive uniform changes in volume, the corresponding change in height increases. This might be a little complicated to sort out, so let's take a closer look. First, let's think about the idea of uniform changes in volume. To do this, let's split the amount of change in volume into two equal-sized parts. So now there are two amounts of change in volume that are equal to each other. These are successive uniform changes in volume. Next, to make things a little easier to see, let's rotate the height bar. Now it's a little easier to see how the relationship between volume and height is changing. For the first amount of change in volume, the amount of change in height is about 3/4 as large as the amount of change in volume. For the second fixed amount of change in volume, the amount of change in height is roughly twice as large as the amount of change in volume. So for these successive uniform changes in volume, the corresponding change in height is increasing. Let's see what would happen if we split the added volume into 5 sections. Now we've split the amount of change in volume into 5 uniform segments. And you can see that the amount of change in height is small for the first segment and then increases for each successive change in volume. So this is what it means to have an increasing rate of change.